Hello, hello. Welcome to my live stream. Just a sec. Okay, hello, welcome to my live stream. I hope my audio is good because I don't have my usual setup. Even the background is not the same as usual. I'm traveling and I just got this lavalier mic here. And yeah, but if something doesn't sound good, please let me know. No data. Hi. Is the sound okay? Do I sound okay? What's going on? Okay. Hi. Can you hear me? If you can hear me, please say something. Having some technical issues here. As I was saying, this is not my usual setup. I don't have all the gear that I usually have. I'm using this lavalier mic and may not sound quite as good. A small echo. Yeah, I think it's because of the mic and because of the room, because this room is not treated. Because this is like has an omni pattern. Hello. It captures basically all the sound in the room, and this room is a bit echoey, so okay. But I'm glad that you can hear me. Do you prefer music or no music? Please let me know in the comments. But yeah, the plan for today is to look into ELF binaries, and until today we've used flat binaries. The main issue with flat binaries is that they don't have any debugging information. They don't have music. Okay, one person voted music. Let's see at least one more person and I'll put music. Okay, so the advantage of having the ELF format is that we can have debugging symbols. And if we have debugging symbols, then we can use the compiler. Okay, music. Just a second. Okay, good. The microphone is not playing back through the headphones, which is great. Just a sec. Yeah, I had something come up and I haven't really had enough time to prepare, so I'm really sorry. Okay, does this sound good? Is this level good? And I hope I don't have that weird filter anymore that I had last time. No, I don't. Good. So last time I accidentally left the noise filtering on and you can't hear anything. Can you hear anything now? Okay, so it looks like people can hear, which is great. Okay, if the music is too loud, please let me know, okay? So your volume was too loud. Okay, good. Glad everybody can hear. So, as I was saying, flat binaries are not as good as using a binary format like ELF or Windows PE, so using like an executable format. And there are a couple of advantages to using an executable format. And the first one is having debugging symbols. which is great. So from now on, if we have debugging symbols, we will be able to debug using the GDB debugger and actually have symbols, see everything, actually debug by going through the C code, which will be great. Finally, yeah, we can finally debug. Another advantage is that now we can configure the basically the location where stuff gets loaded, and the elf loader will have the role of emptying out that BSS section, which is something we did manually before. Also, we can choose which address to load to directly in that elf file. We don't have to modify the bootloader to tell it, okay, I want to load there. So there are a couple of advantages. There's also another advantage, but we're not going to use that right now, which would be relocation. Relocating means that you basically don't know where the file will get loaded. You don't know where the binary will get loaded. You don't know the address. And what relocation means is that the elf file itself will contain a list of addresses where the loader has to go and then modify the address. So if the loader decides to use address, I don't know, 100,000, then it will have to go through all of those relocation places and add 100,000 to whatever value is in there. We are not going to use that feature right now. That's something that makes more sense in the user space, not in the kernel space. In the kernel space, we want to know exactly where we get loaded, because a lot of things depend on that. Our memory manager will depend on where we get loaded, and if we get that wrong, then yeah, we may overwrite something from the kernel, which is something we really want to avoid. Okay, so now let's go through to the code a bit. Actually, before showing the code, let's just go and see what we're dealing with. Right, so the elf format, it basically has a header, obviously, like any file format, and then to load, okay, this is the basic structure. This is a great picture. So at the beginning we have this elf header, which has some useful information. We will use that in order to load it, and then it has some text code header, whatever that means, some data header, and then the actual program is somewhere inside that elf file. It has an offset, it has a length, and we'll see those in just a moment. All right, so let's start by checking out the code, because I used all my checkouts to do all kinds of experiments and recording the next video, which will be about memory management. And I need to create a clean branch. Where are you? Okay, and let's just say live. I have this annoying bug with GNOME that whenever I open a file, I go to file open, this window is not focused. It's really driving me nuts. Okay. Oh. Great, so now we have a clean source code. This is exactly what we have in the repository. So let's start by doing the kernel, because that's actually the simplest. We're gonna start by doing the kernel, and then we will see if we have enough time to do stage 2 as well. I would love to have debugging in stage 2 to be able to go through the code, to debug through the code. That would be awesome. But the main limitation there is that we will have to implement this in assembly. So let's get familiar with the L file format, with all the structures, and by going to the by starting with the kernel. Okay, so you probably already know that I'm using scons for the build system, and the first step would be to change the binary format. And of course that's gonna break everything, but that doesn't matter. So in the linker we have to use elf32 if I'm correct. Okay, let's see if I'm correct. Target of 32 not found. Alright, so it was... let me just find this, because I did this before. Okay. Yeah, no, we're not keeping the bin format for the kernel. We're starting with the kernel. We're changing the kernel to elf first, because this is the easiest. Because our bootloader, our stage 2 bootloader, is written in C, which will make it much easier to work with. And yeah, we will start with that. Okay, let me see if I can find. Okay, let's just look it up. LDL32. It might be this one. Okay, there's a huge list here. So the one we want is LI386. Probably. Okay, let's see if it works. Target not found. Okay, let's look for the output format. L32 dash something, but I don't remember what. Where is the list of... Okay, that's for 64-bit, but I want 32-bit. L32 I386. That was complicated. Why not just use something simple? Alright, let's see that. Yeah, that was it. Alright, so now we have an elf. Easy, right? Okay, now let's try to figure out what this elf file has. So let's start by looking at the binary. So last time I used this imhex tool to look at the binary. I think it should work just fine. The only thing I don't like about this tool is that the font is very small, and I have no idea how to make it larger. Alright, so let's open the kernel. Kernel. Okay, the bin is the wrong name. It's just... Okay, and it starts with elf, which is great. Now, something I noticed that imhex has is these... was it layout or was it something else? No, it's not the layout, it's the pattern. Yes, the pattern. And it already has the pattern for elf, which is awesome. Alright. Yes, we are going to change how we load the kernel from stage 2 to use elf instead of binary. That's our goal for today. Okay, so this is what the structure is. We start with the elf magic string. This is how we can check that it's an elf and it's not something else. And then we have okay, are these not ordered by offset? No, they're not. Okay, so this goes into identity, the magic number, the class, which is probably the elf version, the endianness of the file. This is the version of the elf format. Okay, let's start by creating a new file in bootloader stage 2. elf.h. And And let's actually define the structure. I'm a bit lazy, so just yoink this structure from here. Come on, where is it? Okay, it doesn't give me a structure. Oh no. Okay, I'm just gonna copy this and then I will adapt it to C. And we also want to be attribute fact, because we don't want any padding, because this is a file format and padding would be bad. Okay, we want stdint.h and okay, Visual Studio Code. Include path. I basically moved the toolchain to this. Toolchains, and that should work, hopefully. Did I get something wrong? It did not save. Is there a save button that I don't see? Okay. Alright, so it cannot find this. Yay! Okay. So first we have this 7F magic number. So let's just call it 7F. Actually, let's just use magic and create an array of 4 items, and we can define here (7F) and then ELFD. Okay. I don't know why Visual Studio Code is doing this. Yeah, I'm not in my living room. I'm in another city far away. Okay, then we have this, which gives us the bitness. So int 8 bitness. 1 is 32-bit, 2 is 64-bit. Then little endian or big endian. And yeah, we'll have to declare some enums for all these later. Okay. Then we have the elf header version. API. Did I get this right? These are bytes, right? 0 to 3, 4. Okay, so this is 4 bytes. 1, 1, 1, 1. Now this is some padding from 8 to 15. And how many bytes we have here? We have 16 bytes. All right. Then we have these flags. Okay, so these are 2 bytes. Let's use in 16 lengths. And I will create an enum for these as well. Not there. GCC already defines an elf.h file? Let me check that. I don't think so. No, it doesn't. It does have some elf.h files, but none of them is in the path, the include path. So nope, that should be okay. Alright. Then we have the instruction set, which is another instruction set. Alright, then the elf version. Program entry position. This looks like uint32. Program entry position. Then another uint32. The padding is 8 bytes long. Okay, thank you. Good catch. Program header table position. Okay. Section header table position. I will check them once again after I finish this. Okay, another. Okay, this is architecture dependent. This might actually not be used. Let me just see in IMGUI. So these flags are at offset 2.4, which is 2.0 would be 32 plus 4, 36. Is it the same one? Yeah, okay. And how are the other ones called? After that padding, I had flags. Come on, where is it? Relocatable, executable, these flags. Type machine. Okay, maybe that machine need thing. Or type. Yeah, okay, so it's the type. Let's just call this type then. Alright. And now we have flags, which are another 4 bytes. Header size is 2 bytes. And then we have these 4, which all look like, okay, this is a uint 16. Program header table entry file. And then entry count. Alright, then we have the same for the section header table. Four, 5, 6, 7, 8, 9. Okay, so each of these is 2 bytes. All right, and finally we have this index thing, another 2 bytes. What does this mean? Index in section header table with the section names. Okay, so it's probably where the section names are. Alright, that's fine. Okay. I think we got everything here. Let me just double check the offsets that and the sizes, that all of them look good. So 4 bytes that magic number, then 1 1 1 1 1 1 1 1 1, then 8 bytes of padding, yes. Type, which is 2 bytes, instructions type 2 bytes. We have version 4, 4. Okay, all of these are 4, 4, 4, 4, and then the header size is 16 is 2 bytes, 2, 2, 2, 2, and 2. Okay, so I think this looks good. Okay, now let's add the enums. So for the bitness we have 1 which is 32-bit and 2 64-bit. Okay, then we have the Indianness. Did I spell this right? Yes, so it's double N double S. And the first one will be Little Indian. And the other one is the big. And it should be 2, not 1. Okay. Let's see, the next one would be this instruction set thingy. So L instruction set. And then we have a lot. But what we care about is just x86. So. So x86 would be 3. Okay, there's no point in adding all of them unless we want to support them. Yeah, there is also going to be this one, x86-64. So that would be for just x64, I think is fine. 3E. This would be for ARM, 64-bit ARM, and this would be for the 32-bit ARM. But yeah, for now, I don't think. Okay, maybe I'm gonna add ARM support in the future, so I'm gonna add ARM as well. Okay, ARM Arch 64 BB7, ARM 64. And yeah, let's just be nice and add RISC-V as well, which would be F3. Okay. Alright, let's see what is next. So we have this type, which we should add. Relocatable is one. I'm not sure if these are bits or these are supposed to be values. I have to check that because I'm not really sure. I think that might make more sense for them to be values and not bits, because executable and shared are mutually exclusive. So I think these are not bits, but these are actual values. All right. Instruction set, we already have that, and we have the flags, but these are architecture dependent, so I don't think those actually matter that much. All right. Now there's another tool that I'd like to show you. And let me just navigate to where the code is. Okay, and that tool would be readelf. But we probably have it in that toolchain, so let's just use the one from toolchains. I686L bin, and then we have readelf, and that's the tool. And then we can specify build that kernel.bin. I haven't renamed the file, but I should. Okay, and we want to print everything. Let's just print everything. So -- all, and we get a lot of information. And this is actually very useful for us. Okay, here we go. So this tool basically shows us everything that's in the elf file. And when we write our loader, we kind of have to match whatever is here. We have to make sure that it works correctly. All right, so okay, now let's go a bit into what we have to actually do. So we're gonna go over what we have here. It's the notification sound from GNOME, and I don't know how to say it. Maybe there's a way, but I'm not gonna bother. It's from GNOME. When I scroll up too much, that's what the notification sound is. Okay, so the first step when we load this elf file is to basically validate that we have the correct architecture. So we're gonna check that it is elf32 and not elf64, so we're gonna make sure we are loading the file correctly. Then we're gonna validate if that it's little endian and not big endian, because x86 is a little endian machine. On some machines, I think on PowerPC it might be this way. You can actually configure the processor to use either one, which is kind of cool. But for our purposes, we don't need it. We're just gonna validate that it's little endian. We're gonna validate that the version is 1. I don't know if there are any new versions of ELF, but so far one it seems to be the default. The ABI, it says Unix System V, but I don't think this actually matters that much, because we're not going to run this on our Linux machine anyway. We're going to validate that the machine is x86, so that Intel 8386. Then some really useful information. So how do we actually need to load this file? That's kind of what would be the purpose. So we're going to validate all of these headers first. We're going to validate all of these parameters. And then we are going to look at this start of program headers, which is 52. And same here. If we go into this IAM hex, if we go at address 52, which would be this one, this should be where that starts. 52 bytes into the file. Why is... Okay, so same here. So we have this program header, not that one, program header offset, which would be 1C. Okay. Oh, this one is in binary. This one's in not in binary. This one's in decimal, I think. Although that doesn't make sense. Why is it different? So this tool says that it's 52 bytes into the file, but here it says that... Oh, okay, here's the value. I'm sorry. It's 52, so it starts at address 34. If we look at address 34, that would be right here. Okay, so we look where the program headers begin, and then we start iterating through the program headers. Okay, these are the program headers. And what we have here is this type, which tells us, okay, we need to load this section. Offset would be the offset in the ELF file. So we need to start loading from the offset 1000 in this ELF file. The virtual address would be the address where we want to put the data. The physical address, okay, I'm not sure what's the difference. But then we have file size. This is the size starting from this offset. This is the size of this program that we want to load. But then we have memory size, which is different than file size. And what this is that it also contains that BSS section, for example. So we want to load this. This is basically the amount of memory we want to allocate for it. So the file size is how big the file is, how much data we have in the actual ELF file. But mem size is how much we want to allocate it. Yeah, okay, so the physical address is used for some other machines. Okay, that makes sense. For the kernel, for example, right now we have the virtual address set to 1 megabyte. But in the future, we will want to have this loaded into the upper half. So in that case, the bootloader's role will be to actually enable paging, find some free memory somewhere to allocate for our kernel, find this much space to allocate for the kernel, load the kernel at that address, and then we want to map that address to this virtual address. So this is also really useful when we will do that higher half kernel. Okay. Once we do this, basically everything will be done. All we have to do next is to jump to this entry point address. And that's basically it. This entry point address, it will, after loading all of these program headers from here. So after loading all of these programs, this address will contain basically the address of that entry point of that main function or whatever. All right, it's pretty simple actually. We don't need to go into the section headers at all. We don't need to parse any of this stuff. The debugging information is here in this in the debugging section. Basically, we have all of these debugging sections here, and that's where the debugging information is. But this debugging information is not actually loaded into memory at runtime. At runtime, all we load is just the kernel itself, the code, and the data. And if we go here into this section headers, you can actually see which will be loaded into memory. If we have this X, means that these are executable, so all of these sections contain code. And this W means that it's writable. And A, I'm not sure what A would be. Probably readable, but let me just check. So okay, let's see into those. Okay, it's not even showing the section headers here, because these don't actually matter that much. These are very important for the debugger whenever it tries to load the symbols, but it's not very important for us when we try to load the L file. Let me see if there's anywhere where it says what these section flags are. Okay, I don't really see it. Maybe on Wikipedia. Executable and linkable format. Yes, this is a lot more detailed than what we had on OSDev, which is great. And what I'm interested in is what that W means. But I don't see it here either. Okay, section header. Type. W means... Okay, so... I don't know. Maybe I have to look into the manual of Redel. Not even here, I don't know. I don't see... let's see if my MGUI actually shows that. So, let's go into the section headers. Okay, we have a lot of them. Let's pick one. For example, this fifth one, which contains data. 5. The type would be 4 bits. I can't see it. Okay, so it just contains 1. Yeah, I think 1 means that it's code. Why is it different though? Ah, okay, because I was looking at type and I should have looked at flags, I think. Yes, type is the prog bit. Alright, so I should have looked at the type. That was the issue. I should have looked at the flags. So W would be writable. A means that we have to allocate it. It occupies memory during execution, but if it doesn't have that write flag, then it doesn't have to be writable. And whenever we allocate the pages for loading this L file, we can actually set the correct permissions for each one of the sections. But this is not something we're going to do right now. Okay, so this one tells you that it's an executable, so we want the execute permission. And then these are, I think these are, okay, might be merged. Okay, this is not that interesting. And processor specific. Okay, so basically these are the important ones. These are less important. And if we go back here, okay, so these comments actually have that M and S, which probably mean merge and strings, maybe. I don't know exactly. But in any case, comments would basically contain actually, let's see if it's in here. Okay, and here you can see the actual symbol. So it just gives us all the symbols. Syntab would be this section here, which contains all the symbols. And there are a lot of them, but it doesn't say anything else about the comments, and I don't really see anything here. Okay. But in any case, so this debug stuff is probably used by the debugger. And this comments, I'm not really sure about this. Maybe it's just like this file was generated by LD or something like that. I don't even know what this contains. But in any case, what I wanted to say was that these flags give us which sections we actually care about and that need to be loaded into memory. All right. So let's go ahead and start implementing this verification code, and then we will go into the program headers. All right. Time to write elf.c. Now for the disk API, I have these disk.c. I have these basically. Actually, I have the fed functions, which I think would work great here. Ideally, we would kind of have an abstraction for that and have to add support for multiple file systems, but for now we're going to keep things simple and we're just going to use these fed functions to read the file. Okay. So let's start by open elf open. And let's include elf.h, fat.h, so we have those fat functions. And in order to read the file, we will need okay, this is in the kernel. Let's not look there. Okay, so I opened the file with fat open, and for that I would need this partition. So we can actually use this fat file file descriptor basically. So once we open the file, we will look through those elf headers. Okay, we need some memory here, and let's get some from that memdefs.h. Let's see. So at 30k we have this memory load kernel and memory load size. Actually, how big is the structure? Because I think it might be fine to just add it here. Okay, I think it's best to allocate some memory for it. Elf loads elf, and okay, let's just call this load buffer because it's basically going to be just a temporary buffer, and this is where we will want the actually I think I might be able to use this instead. Yeah, I think I can use this memory load kernel instead. Because I previously used this memory section in main.c, if I remember correctly. Yes, and I'm just loading it there and then copying it to the right address where the kernel should be. Yeah, now the thing is that this fetch read function, it actually needs to have the this pointer to where to load in memory. This pointer has to be in the lower memory region, so below 1 megabyte, because this works in 16-bit mode, in real mode. All right, so we can use basically what I did here. Okay, so what we're gonna do is we are going to read. We also need the partition here. Okay. This is not great, but fine, I'll give you your partition. Okay, and the memory, the buffer. Okay, I'm gonna initialize string 8 load buffer, and we will initialize that to that address from memory def, so memory load kernel. It would be in memory def. Okay, and the first step would be to read the header. So okay, so we're gonna load it first into this load buffer. Okay. And if okay, so we're expecting the size to be the size of the elf header. But if this size is different than our expected size, we will just print an error. No, actually, I don't have like a clean exit. Okay, let's just make this a boolean then, so we can return whether it succeeded or not. So return false. All right. So we are loading from the disk, from this binary file. We are loading the size of this header into this load buffer. Okay, and then we can cast that buffer to that header, and now we can inspect the header and extract the information that we want from it. Okay, and let's start by validating the magic string. And I think we should use compare for that. I don't know if I even have it. Okay, I do have memory compare. And I have that magic string. And the size is 4. Alright, so to make this cleaner, let's create a boolean variable here. And we're just gonna do okay equals okay and this comparison. And we can chain all of these verifications then. Okay, what else do we need to verify? Let's see, so we need to verify that it's 32-bit. If we are going to add 64-bit, then we will also add that check, but okay, and header bitness is 32-bit. Ideally, we should also print messages for each of these things, but that would take too much to write all those strings. Okay, then the endianness, we want to make sure it is endianness little endian. What else do we have? Version, I don't think this matters. Yeah, so I think this would be the header version and this would be the elf version. But if that magic string was correct, then I suppose it should be okay. Okay, fine, I'm just gonna check the version as well. And then we have the elf version. We also want to make sure it's an executable file and not a shared library or something like that. Executable. What else can we check? That the machine is the right one. So what did I call that flag? I called it instruction set. Instruction set x86. Anything else I should be checking? I think that should be fine. ABI version shouldn't matter. This OS ABI doesn't, because I mean we're not gonna run it on Unix anyway, so the rest should be fine. Okay, so now we want to get this start of program headers thing. Okay, so we have the program header table position. Program header offset. And now we want to read those headers. Actually, I don't think I even need to do this. Let's just go and read from the file. Something I don't actually have here is any way of seeking. So ideally we should read the file block by block and reading the whole file in memory would not be ideal, but I don't think we can actually seek, which is kind of a bummer, but I think we should be okay for the moment at least, because as you've seen in this header, the program header comes immediately after the file header, the elf header, and then wherever the data actually is a lot further down the road here. It's like at address 1000. So I think we should be okay with that. Let me see if... Yes, so here we go. This is what the actual structure looks like. So we have the elf header and then we have the program header table. So we should be perfectly fine right now. Because we're not gonna have to go back to read something else from the file. And loading the whole file in memory is not such a good idea. So, that means that we should be okay with this. Okay, so let's add a variable to remember where we are in the file. So we can seek by doing reads, basically. Okay, so initially we are at 0, and if this read succeeds, then... Okay, so... Okay, let's just not do that. So this returns how many bytes it read. Okay, so let's just do int 32t read equals this. Okay, so C doesn't like this syntax, but I think I can do this. Okay, this looks fine. So we read and put it into this variable, and then compare that variable with this size of, which is what we expect. And if everything's fine, we can just increment file pos by the number of bytes read. Okay, and then we validate header, and then we load program header. Okay, so first we need to determine how big this program header is, and we have two numbers for that. So program header size would be program entry size and then entry count. So, but okay, size multiplied by count. And then we need to read again. And okay, so first we want to skip ahead. If this would be greater than this offset is different than... Okay, so in order to skip ahead, we just read program header offset minus the current position, basically. So okay, let's just do file pos, and we read this offset minus the current file position. So we basically kind of want to skip ahead here, and we don't have any seek functions. So this is what we can do to do that, and we're going to load it into the load buffer. Now, something to keep in mind here is that doing this, we will lose this header. So should we do something about that? We have quite a lot of memory actually here. Okay, so let's not overwrite the header because it kind of contains some useful information that we will still need. While I'm not a fan of doing this kind of pointer magic, I don't really have much of a choice here. Okay, so we're gonna increment this by the size of the L header. But it might also create problems because this read function expects it to be aligned to some number. So, okay, I'm not gonna do that. I'm just gonna save whatever we need from this header. Okay, I'll see if I need whatever I need from here. I will save into local variables then, because beyond this point the header is lost. And then we've read these bytes, so now we are at the right position to the file. And now we want to do the actual read. And we want to read this program header size. Okay, so now we have loaded the program header. Next, we need to go through and basically parse all the entries in that program header. Okay, and for that we have this entry size and entry. Yeah, this should not be the section header, but the program header table entry count. Okay, and let's cache these variables because they're gonna be lost. And now we can go through the headers. So, for I equals 0, I smaller than the number of entries, so this entry count, I plus plus. And now we basically need to calculate the offset. So I can just cast this to the header. Okay, so let's add the header structure here. So like dev struct elf program header, and I'm gonna copy it from Wikipedia. I have no shame. I'm just gonna copy it. Okay, alright, this looks confusing. Why are there so many numbers? Oh, okay, it's this table. Okay, so I'm just gonna move this out of the way. Okay, so what we have here is a pair of numbers, which is the offset for 32-bit, then the offset for 64-bit, and then the size for 32-bit and size for 64-bit. Ah, okay. So, first we have this, which would be the type, which seems to be a unit 32. Let me just verify that because I'm confused. Okay, it's 4. Type. Is this the right structure? Yes, is the program header. I don't want to accidentally do the section header and then not have it not work. Okay, so the type, then we have flags. Okay, why is this? I have to decipher this table, which looks a bit confusing to me. Why was it written this way? Okay, so at address 0 we have the type and then we have the flags. Segment dependent flags. But okay, so this is only for 64-bit, if I'm not wrong. Because this one is 0 and has the length 4, and then the next one starts at 4, so I would say that this is 64-bit only. The flags are, these are 64-bit only. Okay. Offset, which gives us the offset into the file. My playlist, sure, I can give you the playlist. I'm basically using just songs from the YouTube audio library to avoid any copyright issues. But yeah, sure, I can share that with you. You can find all the songs in the YouTube audio library. I will write that down and put it in the description or something like that, okay? Sounds good? Okay. Music is too loud? I can lower it a bit, no problem. But I'm glad it sounds good and it doesn't sound muffled like it did last time. Okay. Alright, so then we have the offset. Okay, I already added it. Then the virtual address. So here 32 virtual address. And then the physical address, which is not important. Then we have the file size, which I assume is also enough 4 bytes. So it looks like everything is 4 bytes here. Yeah, everything is just 4. Just 4s everywhere. So uint 32 everywhere. That makes it easier. Okay, so virtual address, physical address, then the file size, then the memory size, and then the flags. The segment dependent flags. Oh, come on. What does that even mean? So we have the file size, the memory size, and position for 32-bit structure. Okay, I guess it's flags. I don't know what that means. Then we have this alignment. And this basically tells it when we write our allocation code that will find some place for the kernel. This align will tell it that, okay, I want it to be aligned to that address, to be a multiple of this number here. So as you've seen, this one is 1000, so which would be 4096 would be the equivalent in decimal. Yeah, I think that's the one. Yep. But we can change that if we want. Okay, so the alignment, and is there anything else? No, the end of program header size, whatever. So okay, I already have the. Okay, and now we have these type flags. Elf program type. And then these. Okay, and can I use some magic here? Like, okay, so I can select all of these. Okay, nice. So I can write all of these at once. I already wrote the null and elf program type There we go. That's more like it. And then that equal sign. Yay for multiple cursors. And then I can just paste all of these numbers. Although some... Okay, let's see if this... No. What are you doing? Yay, it worked. Perfect. Nice. So I don't have to... Okay. And okay, let's just add the comments as well because these seem useful. Loadable segment. Okay, so this type, it looks like it has this lower number. Let's just get rid of all that useless stuff. So it's more readable. So, and this might, I don't know what this is. I don't think it even matters. Anyway, so where was I? The dynamic thing, interpreter information. I think I'm kind of lost here. So 4 is auxiliary information, 5 result. Six be this thing. But in any case, these don't matter as much because what we care about is just looking for those load segments. We don't care about the rest. Ah, okay. I think this might... I don't know what this means. I think reserved inclusive range. I was thinking that maybe it's the fact that the kernel is in the upper half, but I'm not really sure. Okay, whatever, doesn't matter. Okay, so we have the type, the offset. Okay, the rest are pretty easy to figure out. And the flags, let's see if there's anything interesting there. Flags, readable, writable, executable. Okay, whatever. It's fine. Okay, so now let's go back to the code to this. Okay, so let's get the header of program header. And this will be at the position given by load buffer, which is where we loaded the program header, which we have to add I multiplied by the program header table entry size. And the reason why we do this instead of creating like an array of ELF program headers is that, okay, so if maybe in version 2 of the ELF format, maybe they will add some additional fields, and having this program header table entry size and using this will prevent us from having the problem of basically reading garbage. Okay, so the offset would be this one, which is the beginning, plus I, which would be the iterating index multiplied by the size. Good. Okay, now if program header says that we need to load it, so if the type equals ELF program type load, then we need to load. Now here's a bit of a tricky part. What if that virtual address is where the stage 2 is? What do we do then? That might be a good idea to do some validation there. So to do validate that the virtual address in... Okay, so it's this interval, the interval between the virtual address. Okay, so verify that the program does overwrite the stage 2. And yeah, I'm just gonna leave this as a to-do, but it might be a good idea to do that. If for some reason you decide to load that file somewhere else, at wherever the stage 2 might be, then this validation will save you. But I'm not gonna do it. Okay, so now we know prog header. And then we have the virtual address. Okay, so the first step would be to clean up that memory region. So let's just do memset that virtual address. Let's set that to 0, and the number should be prog header memory size. So we are preparing the memory. We are cleaning everything up. We are setting everything to 0. And then we need to load. Now, for loading, we also need to do this seeking, which is a bit annoying. Because when we can't seek back. That's the annoying part about this. Okay, so is there an easy way to solve that? Okay, so I'm not going to do anything here. So proper seeking, because right now if our program has more than one headers and they're not sequential. So if one of the program headers says to read from the, I don't know, address 1000, and then from address 10,000, and then the second program tells us to read from 1000. That would be bad. We would need to seek back to the beginning of the file, and we cannot do that because we don't have that implemented in our fed driver. Implementing seeking would not be a bad idea. It would help us a lot. But for now, let's try to do it without. There is one way to do that. We can just, okay, if we have to seek back, we just close the file and open it again. Easy solution? Easy solution. In that case, we would have to load this file a bit differently. So instead of passing the fat file descriptor, we would pass the path. And then we would do the open here inside this function. So actually, let's do that. I don't think that's a bad idea. Because that's all I have to do, just fed open. And the path is passed as a parameter. Okay. So, okay, again, we have the same issue we had here when reading the header, because now if we read something into this memory address in this loaded buffer, it's going to be overwritten by the whatever we write there. So let's address that by... Fine, I'll just create a new memory section. Because it looks like I don't have a choice. Is this header large? Okay, yeah, it might actually be pretty large. It might have like... I mean, in our case, the kernel is very simple, as you've seen. It has a single program header. It could become more complicated, but I don't know if I see this as being a big problem. Okay, let's not override it anyway. So I'm gonna allocate some new memory for it. We have plenty of memory, don't we? Okay, so let's call this elf data. Elf address, okay, and we're just gonna use this address for loading stuff from elf, and then we're gonna use this section for actually loading the kernel. And now we don't have a problem. And there's a cat watching me. It ran away. That was weird. Just a cat showed up on the window. Sorry, didn't react fast enough to move the camera so you can see it as well. Okay. Okay, so now instead of using that memory load kernel or whatever, let's just use memory elf address, and let's call this, instead of load buffer, header buffer, because it contains headers. All right, and I'm gonna create another one for the load buffer. Yeah. That has the kernel thingy. Yep. Okay. Okay, so we have cleaned up the memory, and now we need to basically seek that file and go to the right place. And what I'm going to do is just close the file. So after reading the program header, I'm just going to do at close of fd, and here I'm just going to do fd equals that open. It's not the most efficient, but I suppose it works. Yeah, we should implement seeking. It might be a good idea to implement the seek function in our fat driver. Okay, so yeah, that's a to-do here for another day. Okay, we are going to open the file, and then we want to basically go forward. We don't have seeking, so we just have to read until we get to the right position. So we're going to read some junk until we get to the... Okay, so left. Okay, so the left to read is basically just this offset, right? It's the prog header offset. So while prog header offset is greater than 0, we are going to read minimum between what's left of the offset or the buffer size, and let's have the kernel size, memory load size. That would be the maximum. We don't want to go above this because that will create a lot of problems, so we want to read bit by bit, and that's how many bytes we want to read. Okay, 32 read, read, and then Yeah, this should be a pointer. I don't know why I did not make it a pointer. Because it contains a lot of data and I don't want to copy it. Okay, not that much data, but still, I don't want to copy it. Okay, part. And same here, part. And we want to read from the file fd. The byte count is should read. And the data out would be that load buffer. Okay. And then we're gonna validate it read properly. So if it is different, then should read. Then there's the read error here. Just gonna print the error message. Okay. Okay, so after going through this entire loop, okay, so we now have to remove this read stuff from the offset. Okay, I'm just call this bad seeking. Ugly, nasty seeking. Okay, and now we should arrive at the actual program. Okay, and the approach we do here is kind of similar. So while the size, the file size is greater than 0, we will okay, so for this virtual address, I should create a pointer. And cast this to a pointer. I think this code is very messy and I'm gonna refactor it at some point, but it is messy right now. Basically just implemented everything inside this function. I just realized. Okay, and we can just use this virtual address so we don't get that warning message from memset. And then here we are going to read while the file size is greater than 0, we are going to read this number of bytes. We do the fat read just like before. If there's an error, we print the error message, and then we decrement the read from file size. So file size minus equals read, and then we want to copy all this data that we basically loaded here. So copy. The destination is this virtual address. The source would be load buffer. The number of bytes would be how many we've read. And then we have to increment this virtual address by read as well. Okay, so what we're doing here is we are going through block by block because we are limited by how much we can allocate here. And I might have talked about this earlier. Since this code, the load code is implemented in real mode, then we cannot cross the boundary of a segment because bad things will happen. So this will get converted to segment 4000 and offset 0. And this size is basically the size of an entire segment in real mode. And bad things will happen if we make this larger. And we don't want that. Okay. So okay, we are calculating. Okay, so however much we are left from that file size, the minimum between that and how big our buffer is, Then we do the read operation. Then if read is not how we haven't read how many bytes we were expecting, then we are printing this error message. Then we are decrementing. We are subtracting how many bytes we've read from the file size, and then we are copying the data to the final location, and we are incrementing that virtual address. Okay, this looks pretty good so far. I think it's almost done. There's one more thing we need from the header, and I'm going to save it here. Entry point. Program entry point. And actually, I'm gonna pass that as a parameter to this elf. Let's just call it read. Void entry point. And this will be a pointer to a pointer, and we want to modify this pointer so that it points to the right pointer, right? So entry point is okay. So what we are doing here, we are passing a pointer to a pointer. So let's imagine that this is not void, but this is the uint32, right? Let's say that this is not void star, this is uint32. Then how would you write the data to this value? Star entry point, so asterisk entry point equals whatever you want to write. In our case, that would be that program entry position. But in our case, we want to cast that to a void pointer. So this is a pointer, and we want to modify that pointer, right? So, okay, just to make this really clear. So we have a little whiteboard here. So let's say that this is our memory, and this is where we loaded the kernel. Okay, I'm just gonna write this down. Okay. Is this visible? I think so. Okay, so we have the kernel and we have that entry point, right? And now we want, this is basically what we are reading here. And this void star is a pointer which is somewhere inside wherever this code runs. So that is a pointer, right? It's a void pointer, so it's basically like an integer that will point to that entry point. Yeah. So it will point to that entry point, right? And now we want to modify what's inside this void pointer. So how can we do that? By adding another asterisk. So that's kind of the idea here. I hope this was clear. Okay. In fact, I think we can just pass uint32 because we're gonna cast to a function pointer anyway later, so yeah, let's keep things simple, I guess. But okay, so the reason why I wanted it to be a void star is that we might want to run this code in 64-bit as well, where the pointer size will be different. So there's an advantage to doing it this way. Okay, so I'm gonna leave it as a void pointer. Okay, so we have the entry point, we have read all the data and placed it into the right place, and we've closed the file, and I think we are good to go. Okay, so here in this loop where we are opening the file, we would also want to close it. So before this little reading while loop, this read program loop, we are going to close the file. And I think we are done, and we can return true. Let's compile this. Okay. Yeah, this should not be a const pointer. Neither should this. Expected void, but argument is of type that. Okay, so it's that constancy issue. Implicit declaration of printf. Okay, hex escape sequence out of range. Yeah, I thought something was odd about this, and I don't. Why is it doing that? Shouldn't this be like a hex number? Okay, hold on a second. Yeah, it's also doing something to the E, which I don't know why. Hold on, let me. Should work, but why is it interpreting more characters? Okay, so with 0 is octal, with X it should be hex. I still find this weird. Okay, so what we can do is just separate this like this. Let's see if that fixes the issue. Yes. Okay, then we have some issue with fat open. Yeah, so instead of passing the disk, I passed the descriptor, I think. Line 62. Yeah, so here we should pass the partition or whatever. Okay, anything else? Implicit declaration of function min. Oh my. Do we even have that? Minmax.h. There it is. Okay. And we have success. Okay. Now let's go into main and implement and call this function because I haven't done it yet. So main.c. And instead of just doing this, what I'm going to do is first include l.h and load. Read. What did I call that function? Okay, I haven't added it to elf.h. That was my mistake. Alright, and for bool, we actually need std there. std bool. std bool.h. Okay. For partition, we need that what did I call it? Partition. What did I call it? Disk.h or mbr.h. Okay, this code is a mess. I really want to reorganize everything and clean everything up. Okay, so that was good. Now let's call the street function from main. So instead of doing whatever we did here, to load the kernel, I am just gonna do elf read partition, and the path would be this one. And we also want to pass the entry point, so that would be this one. Entry. Okay, and if this fails, we want to print a message or something. And what did we do here? Go to end. Okay, and if everything goes right, then all we have to do here is just call this kernel entry. Okay, done. Let's see if this works. Okay, we have some... Oh, okay, it doesn't like that I cast this to a... Because this is not a void, this is whatever this function pointer is. So let's just cast it to a void star star. But other than that, it looks good. Let's run this. And here it is, it works! Oh my god, I don't believe it would work from the first try without testing anything. Incredible. This is incredible. I surprise myself every day. Okay, that's great. So we have loaded the kernel, we have converted the kernel into the ELF format, and we have loaded it, which is great. Something we also want to do here is to clean this up a bit. So we basically have in the kernel, for example, the start function is inside this entry section, and this was required in that flat binary because we needed to put it right at the beginning of the file. But now this is not necessary anymore, so I can just delete it, and I don't need this anymore, this BSS start stuff. Okay, I do need to call the global constructors. Okay, that's something I still need. From the linker, I can also delete this entry section because it is not needed anymore, because we have defined the entry point to be start. So let's get rid of that. And now this looks cleaner. Okay, and let's see, what else do we need to do? Yeah, so I don't like the fact that we are compiling an ELF file, but it has the extension .bin. So let's change that. Instead of kernel.bin, it's gonna be kernel.elf. And wherever it says kernel.bin, like over here, let's just call this kernel.elf. Okay. And let's give this another go. Commands run, and magic happened. We have a kernel which is an ELF file. So the cool part about this is that now we can use that ELF file to obtain the debugging information. So let's go to that debugging code that I wrote. So debug.sh. And here I have this little script that I wrote for GDB. And now we're gonna look into the syntax on how to add symbols. Okay. Okay, so add symbol file. Let's hope that this works. I'm not sure if this is the right or just symbol file. There's also a file which uses file name as the program to be debugged. Okay, let's try with symbol file. I'm not sure if typo in warning string. Yeah, I know about the typo. I don't care about that. I'm just gonna delete that the moment I start making changes in the kernel. Yeah, I don't care about. Yeah, he's talking about this warning here. Happy now? Are you happy now? I've done this. I've changed this. Are you happy? Okay. This is just some testing code, and whenever I'm gonna do something, I'm just gonna delete all of this because this is just for testing. Okay, so we want to add. Okay, let's see if this works. So, symbol file, and the path would be build i686 debug and stay kernel.l, and let's see if this works. I'm not gonna set the layout to assembly anymore. I'm gonna comment this for a moment. Okay, let's see if we have debugging set now. Yay, we're all happy now. Okay, and let's continue. And okay, let's see if we can break it start. And there we go. Breakpoint 2 at this address in file main.c. And let's see, run or continue. Okay, so it stopped at 7000. That's fine. And there we go. We are now at this start function inside source kernel main.c. Now there was a integrate GDB with VS Code. That would be a great idea. Okay, I will look into that in just a second. There was a GDB cheat sheet, a very useful file. Okay, so GDB has a text user interface. Mode. Actually, let's not debug it in this VS Code window because this will not work properly. Let's debug it in this terminal window because this will work better. Okay, const debug. Okay, we're gonna break at start, and it found our symbol, and we're gonna continue all the way to start. And combination, I think. Okay, let's see. Mode. Okay, so there's a command line flag, but I think that there's a key combination. Control X, Control A. Control X, Control A. There we go. And let's go. Next, hull initialize. Okay, we want to step into. This is quite something else. This is a different. This is a totally different debugging experience. Okay. Okay, let's go into our printf implementation and see if everything looks good. Okay, there we go. We have variables. We have module is main, the level is LVL debug, and the format is this. Okay, this looks good. Okay, let's go to something that... Okay, I don't have anything that has arguments here. Okay. Okay, so let's see, printf. Okay, this is the format, and now we have the states. Now this is a completely different debugging experience. Okay, let's see how we can actually integrate this with VS Code. That would not be a bad idea, actually. Okay, so let's see. Run script. Debug C++ in Visual Studio Code. Let's see how we can do that. Okay, the debugger path, whatever. Additional symbols. But I don't know how I can get it to connect to camel. That's kind of the main. It does have that pipe transport. Pipe transport. Okay, so that one is through SSH, but that's not what we want. Okay, let's see if maybe we can find VS Code, debug. Maybe there's an easy way to integrate those two. Okay, install all the dependencies. Okay, and here we go. cpcc. Okay. All right. So it connects to the server address. That's the. Okay. Then we have this program, which probably gives it the symbols, arguments. And yeah. Okay. Let's see if we can get this to work. But we will need to start that debugging port manually, or I don't know, maybe do some. Can VS Code run like a command before? I would be curious about that. VS Code run command before debug. Okay, so basically, okay, so we basically need to create it as a pre-launch task. I'm not going to create a pre-launch task for building. Okay, let's see if we can get it to work with that. So I already have this debug script. Okay, so basically I've set it to use GDB with stdio, but we won't be able to do that, I think. Yeah, I think YouTube is filtering the links, so you can't send any links. Okay, so what we need to create in Visual Studio Code to integrate this nicely would be to create like a task, which is set as a pre-build, a pre-launch task, right? If I am not wrong about that. Actually, I'm not sure what this is. Okay, let's create this debug configuration first, and then we will see. So run on debug and add configuration, and let's use GDB attach. But we're not going to attach to a program like it's expecting here. Okay, so let's call this OS debug. cpp dbg request is launch. Okay, so let's see. Request should be launch. Okay, the program will be... I'm just gonna give it the kernel. So workspace folder build i686 debug kernel.build. Okay, then we need to set this debugging server address. Okay, stop at entry. I think, yeah, okay, we can just disable that as well. Okay, and we have the setup commands. Nice, nice. I think we might be able to use those. Okay, so kernel debug. Did I miss anything? Rx should be empty. Environment, external console false. Okay, I'm just gonna copy the rest. Everything. Okay. Yeah, I think this looks good. And now for the setup commands. We would like to I wonder if these are command line arguments. Pretty printing is a feature that I don't think we're going to be able to use. So, okay, disassembly flavor should be Intel. That's great. Okay, so let's go to GDB command argument. Actually, I think I might be able to... Okay, I'm gonna create inside this VS Code a file that contains... Okay, so to basically give it a script, what you can do is run it with -x and then give it a script. And what I'm thinking here is to give it a script that has this, but I think, and if it has this target remote, then it might actually run the camel for us, so we don't have to do anything. And then also this okay, this is not as nice as I thought it would be. Okay, what I can do is, so when you run debug, for it to put the file into this VS Code folder, I think that would be a good idea. And every time you run this, it will just place update this VS Code file, basically. And we don't have to delete it. No, we don't. Okay, I'm just gonna remove this break because I don't want it to break at the moment. I just want to see if this works. Okay, so to run this, I'm just gonna use -x and then this file. Okay, so first I'm gonna run const debug, and that will generate that gdb script.gdb here. That's it. And I'm just gonna tell give the setup command to run this -x and then workspace folder / VS Code gdb script.gdb. I have no idea if this is gonna work, but let's give this a try. And I don't need this debugging port at all, because I had... okay, I deleted it by accident, but I don't need it, because we will not be attaching to the debugging port, but we will use that stdio feature that Camo has. Okay, let's give this a try and see what happens. I have no idea if this is going to work. Segmentation. Okay, this did not work as expected. Okay. So it does look like GDB did not load the file correctly. All right, so let's stop this madness. And let's figure out another way of doing this. Launch.json, setup commands, okay. Setup commands. Okay, in order to set up... Oh, okay, so I think these are actually just commands that we give... So what I would do is just place all of these files here. Where are you? Launch.json. And the text, is that the text? Okay, so I can just have multiple commands. Okay, here we go. Custom launch setup commands. That's the one. Okay. Custom launch setup commands. Okay, and let me paste the command. So first we want to add the symbol file. Now, okay, is there a command for GDB? GDB command. Is there a command to load, execute a file? Because that would be nice. Execute script command. Okay, source and then command file name. There we go. There we go. We don't have to type in all of these manually. Great. So the command would be source. And then this GDB script. We don't want to ignore the failures because that would not be great. Okay. And after doing that, there was another command here that I saw, which would be this launch complete command to exec run. So whenever it's done setting up, it should launch. It should basically run the program or the OS or whatever. Okay, let's see if this works. Unable to start debugging, specified argument was out of range. So the program has exited with code. But why is it trying to run it as an elf? I don't understand that. Did it run that script? I wonder. Terminal, okay, output. There's nothing from the debugger here. And I have no idea if it's actually ran that properly. Okay, it's just trying to execute. It's not helping. Okay, maybe that launch complete command is the problem. Let's just set it to none. And see what happens. Nope, still no. Why doesn't it give me a log? Oh, that's annoying. It should give me a log of everything it did. Of everything. Oh, okay, engine logging false. That's why. Okay, let's do true because I want to see all the logs. I want to see everything it's doing. OS debug. Okay, so it ran GDB. And that's it. It didn't execute that command, which is weird. Why didn't it execute the command? Yeah, it did not execute the command. Custom launch setup commands. Let's see, did I spell this right? Custom launch. It has a text. Yeah, I think it's... So, why are you not working? Okay, maybe we don't need to provide the launch setup commands, but the setup commands. Okay, let's try that. So let's just say setup commands, and then for the custom launch setup commands, I'm just gonna set it to empty. All right, and the text will just be nothing. Nothing. Is there anything wrong here? Configurations. Why is this one to the right? Okay, I think this one needs to be tapped a bit. There we go. Okay, let's see. Command text was out of range. What did it say? Maybe something in the launch JSON file is wrong. Unable to start debugging. Parameter command text. Okay, let's see. Where is that? Command text. The launch complete command. I've set it to none. exec run. I don't think that's gonna work, but let's see anyway. I doubt it. No, it's something else. It's some command. Man, this is annoying. Okay, so is it this setup command or is it this one? Let's try to comment one of them and see if we get the same thing. Okay, so we got something else. All right. Source, whatever. No such file or the directory. Okay, so that's something else. So it tried to run source, okay, to that file. And then, okay, so it found an error here. It doesn't like that. Because this kernel.l file is not in the right path or something. But didn't we set the current working directory to be the workspace folder? So why doesn't it find it? Okay, I think there was an option to provide symbols. Symbol search path. There we go. Let's see if that works. It's a lot of trial and error. I mean, not all the stuff is very well documented, so. What is it? Oh, property is not allowed? But where is it allowed? Where is it allowed? Oh, okay, so this one is probably up here. No, should be okay. Symbol search path. Okay, maybe that one only works on Windows. Okay, there's another option. Okay, so symbol options, search paths, still not allowed. The question is, where is it allowed then? If it's not allowed. I don't see anything here in the documentation saying that this only works with Windows. So configure debugging. Okay, there's an solib search path. Okay, maybe it's using this one, I'm not sure. Symbol load info. But that doesn't help. Okay, this thing is annoying. So it doesn't allow me to use symbol options. I think that might actually only work on Windows. Because that's how Windows works. Okay, so it is running our script, but for some reason... Okay, what if I don't provide the path, the absolute path? What if I give it an relative path? Yeah, it cannot find it. Why? Just why? What current working directory is it using? Because that doesn't make sense to me. All right. Okay, in that case, what I'm gonna do is, let me think. I could set this symbol file to be an absolute path. I mean, I don't think there's anything wrong with it. So yeah, okay, let's do that. So here, let's just do dw d/build/ whatever. And I think that should fix it. Hopefully. Hopefully. Let's see. So on debug, and that will regenerate this GTP script. That's all we have to do. What errors? Did it say any errors? I don't see. Okay, it's just from scans, whatever. Yeah, so now we have an absolute path. But yeah, maybe this will not work this time, because this is not an absolute path. Okay, let's see. Fine, just giving it absolute paths everywhere. If that's what it wants, that's what I'm doing. Okay, regenerated the file, and now let's run. Yes, we have success. I don't know yet. Let's see if we can reach. Okay, we've already booted. So let's try again. Yes, it works. So now we have full debugging support in Visual Studio Code, which is awesome. So, okay, let's just go and see what variables we have. Module, main, debug level, level info, format. That's more like it. Yes. Yeah, it worked. All right. Yeah, we had to do some workarounds, but at least we have debugging support in Visual Studio Code, which I think is great. This is awesome. Okay, I'm committing this code now. I don't know what this is. I'm deleting it. Discard. All that, elf support, and full debugging. VS Code debugging. I think that this was a success. Commit. I think. What could go wrong, right? Just commit everything without checking. What could go wrong? And push. There we go. You have the code now. You can check it out for yourself. Let's see. Yeah, 2 hours and 30. I think this is fine. This is a perfect length for a live stream. But yeah, I'm happy that worked. We don't have time anymore to do the stage 2 as well, to have the stage 2 be an ELF file as well. Maybe another time. But I'm glad this was a success. I'm very happy that it worked. And yeah, it's great that we finally have debugging. We finally have a much easier way to debug. We can actually use GDB, we can use debugger functionality, and that's great. This is one of the biggest advantages of ELF files. Now, just to tell you a few more things. Okay, there we go. So if we go here into kernel and kernel.elf, you might notice that this file might have actually grown a bit. Kernel.elf is 68 kilobytes. What we could do here would be to strip the symbols. So we could have two ELF files, two different ELF files, one to put on the actual disk and one that we just use for ourselves, right? That for debugging. And the one that we put on the disk, we can strip the symbols from that file. the advantage of doing that would be to have a smaller file. But I mean, 64 kilobytes is not that much. But we would save... Okay, let's see how much we would save, because I'm curious as well. So... there's a tool inside our toolchain, which should be strip. And I think all we have to do is just give it the path to the file. Can I copy the path from here? Maybe I can drag it. Yes, we can drag it. Good. And I don't want to strip. I mean, actually, it's fine. Okay, and now the file is stripped. So before it had about 68 kilobytes, and now it has 20 kilobytes. So that's a huge difference. Those symbols are really big. And yeah, maybe you want to have a smaller image, or maybe you just want to have like a release version of your software, which is, but you want to still maintain symbols so that you can debug if something goes wrong. And this is a great way of doing that. What I would do here is I would create... Okay, let's actually do that right now. So in the kernel scan script, let's create a second kernel, which would be kernel script. And what we need to do here is to tell cons to take this file and then run strip on it. Okay, let's see if there's an easy way to do that. Okay, so what I'm thinking is that this strip program, let's actually check the menu for it, because man strip. Because okay, so we can actually change the target. We can set -o and set a different file. So that way we don't overwrite the original file and we keep all the symbols there. But we do generate a stripped file which doesn't have symbols. Yeah, now as I mentioned, you can copy this stripped file to the disk and have that be loaded on the actual disk. But when you load it into GDB, you use the non-stripped file so that it finds all the symbols. That's the best way of doing both, basically, of also having symbols and also keeping a small file size. Okay, so what I am gonna do is kind of what they did here. So what they did here was they created this strip tool. The com is basically the command for strip. And then strip com string is the string which is basically gonna be shown on the screen. Okay, so let's try to add this as well. Okay, we have to go to the main construct, which has all the commands here, and we already have strip for the host environment, and we already have strip for the target environment. What we don't have is those other arguments. So strip com, which would be the command. Okay, let me think about this for a second. I need to read a bit about these actions and what they do. So sconce action, because I want to really understand it really well before I do this. Okay, this is annoying. This is not the actual documentation. I think it's easiest to just go to Scon's website and look at the current documentation. This user guide is what I'm interested in. And here, action. Okay, fine. I'm just going to use the command builder. That's it, I think. Yeah, I'm just going to use the command because that one is a bit easier for me to use. Okay, so to do this, all I have to do is just run command, and now we have to give it the command, the actual command, and then the arguments. Okay, let me see how command is used. Right, builders that execute external commands. Okay. Just want to use the command builder itself. Okay, so here's the syntax. This is what I wasn't sure how to do. So first is the output file, then the input file, and then the actual command. $source would be the source file, which would be this one, and the target would be the output file. So all we have to do is run command. The output would be kernel stripped.elf. The input would be this program that we have above here, the kernel. And then the actual command to execute would be that the strip, which is a variable we have in the environment, and I think we can actually use it like this. -o would be target. I think it was capital O, if I remember correctly. So where did I have that manual? Here. So it's capital O would be the output target. Oh, hold on a second. I think it might actually be just -f, but I'm not sure. Okay, let me just look it up. Strip symbol. I think it's -f. I'm not sure, but I think that's the one. It's annoying because I don't see any examples of how to use it. Strip command examples. There we go. So okay, but how do we not overwrite the original file? Shield. Okay, there we go. So it's -o, but not capital O. That was hard. So it's apparently this option, -o file. And I don't see it. Okay, anyway, so -o target and then source. Let's see if this works. And I'm gonna export the stripped kernel as well. I'm not sure if it's gonna create it because there's no dependency on it. Basically, it creates kernel because this image, this disk image depends on the kernel, and that's why it's building that. But I might have to do always kernel stripped. Okay, the syntax is not this, so it's maybe env dot always. There was a command with always, but I don't remember exactly what it was. I've used it here, always builds. There we go. Now, this is not ideal because... Okay, I think this is fine. It will run it every time, regardless of whether this changed or not. But let's check it out and see. So I should... Okay, let's check it out and see if we have two files, a kernel.elf and a kernel strip. Okay, I think it might still be the old file. Just delete it and run it once again. And... Okay, now it has generated that stripped file. So kernel is 68 kilobytes and kernel stripped is 20 kilobytes, and it doesn't have symbols, which is great. Okay, so I'm not really sure how to make it build this if kernel changed. Top level, what is it called? Dependency. Okay, that's a good question. How do I force it to build that file, but without... But only if the source changed. Top level targets or something like that. Okay, so how does it decide which are the top level target? Okay, so it's default. Yeah, all right, that was the one. So it's not always built, it's default. So what this does is this will be part of the build process, but only if something has changed. You can see here it checks that, okay, this is up to date. It's checked the kernel stripped. It's checked the kernel, nothing changed there, so this one is also up to date, basically. That was the keyword I was looking for, and I couldn't find it. Not really. Okay, let's see a So somebody asks if ELF is a standard thing for an OS to have. I would say that it's not standard to use ELF in particular, but it is standard to have an executable format. Having an executable format that allows you to have symbols is a huge advantage. And there are two main executable formats in use today. There's the ELF format, which is frequently used on Linux, and there's the PE format, which is the one used on Windows. And both of these can contain symbols, both of these they both have a lot of features. There are some older formats. There's the A.out or whatever it's called, which is an older format that was used on Linux. It's kind of like ELF, but a little bit simpler. So yeah, I hope that answers your question. NT-kernel is actually nt-kernel.exe or something like that, or DLL, which is a binary format. It's an executable format. NTO's kernel.exe. So it is an exe, yeah. To add macOS support for the build, you mean, right? For the build process. In this live stream, not really, because it's kind of late already. It's like almost midnight for me, and I will end this. But maybe in a future live stream, I will. Yeah, I promise. In a future live stream, I will look into adding macOS support. Something I don't have right now, and the reason why I didn't do this earlier is I don't have the macOS VM. It's on my NAS, but I'm not at home right now, so I don't have access to it. And it's like 150 gigs, so it's pretty big. But yeah, I will prepare a live stream where I add macOS support and I add all the major distributions, because I know that when I made the change to scones, I kind of broke support for some of the distros that I used to support. Yeah, that's something I'm planning to do. And I'm also planning to add a Docker file to add support for building with Docker. The advantage of that is that okay, so the advantage of using Docker is you can reproduce the build every time. So even if you are running Gen 2 or whatever, some very different distro some obscure distro that doesn't have all the tools that are present on the major Linux distributions, you will still be able to build this project using Docker. Yeah, that will be for a future live stream though. If there are any other questions, I'm gonna look a bit through the comments to see if there's any questions I haven't answered yet. Okay, so for the playlist, yeah, I promised I would take care of that. Let's see, this is my little playlist. Let's see if I can generate a playlist out of that, maybe. Playlist live stream, and can I save that file as anything? Okay, it's not, doesn't seem to be working, but I do have a list of all the files, and okay. So the music is, let me see, because I don't remember what folder I put this in. Okay, there it is. It's basically this folder and this folder. I'm gonna make a list of these and open in terminal, ls ls-1, And let's put that into music.txt. And let's do the same with the other folder. Okay, and I'm gonna create a gist of that, and you can find a link then. Okay, I'm not signed into this. Okay, so you can find it at this gist. I'll put a link in the description if that makes you happier. Okay, let's see if there's any other questions. Okay, I think that would be all for today. No more questions, so thank you very much for watching, and I will see you if everything goes right, in maybe 2 weeks. That's when the scheduled live stream will be, but as everyone has mentioned in that poll I created, you want to see everything I do you want me to live stream everything I do, so maybe I will have some live streams that are like not pre-planned, right? Okay, so yeah, that's it for today. Thank you very much, and see you next time, I guess. See ya. Have fun coding, have fun making operating systems. Goodbye.